All right, so let's go ahead and change gears into the world of collisions, but still be thinking about this cool little birthday paradox in the back of our head. So in general, what's going to happen is that we're going to take some random input and we're going to funnel it through one of these hashing algorithms, and it's going to kick out some output. This output is going to have a specific length. What that means for us is that we're going to have a finite number of possible hashed values. That number is going to function just like the number 365 did in the birthday paradox. That's my total number of possibilities that I can work with. So if I go back to our quote unquote bad hashing algorithm, the thing that took all of those characters, converted them into their ASCII counterparts, and then just XORed the whole lot together and then kicked out that answer, we don't have a ton of outputs possible. So if you remember hello world, that thing got bad hashed into the number 32. And if I convert that into binary, it's going to be 1 followed by 5 zeros. So if you paste this on this nice little tape that's going to have these 8 little bins, you can see a 0, 0, 1, 0, 0, 0, 0, 0. So then if you play the game of how many ways are there to fill those little boxes, you can see that there's 2 objects that can be put into each of those, either a 0 or a 1. So we have 2 choices for each of them. So in total, I'm going to have 2 times 2 times 2 times 2 times 2 times 2. So 8 times I'm going to multiply the 2 together to give me 2 to the 8th, or 256 possible outputs. So our bad hashing algorithm has only 256 total outputs. So technically less than the number of days in the year. So what that means for us is that if I try to play this collision game, I can start to basically use some of the numbers that are similar to the birthday paradox. The idea is that if there's 256 possible outputs, how big of a list do I need to use in order to have a 50% chance of collisions? What about to have a 70% chance of collisions? What about a 30% chance of collisions? So in general, what I can do is I can build this nice little table just to kind of get a feel for where I should be living. So if I have 8 bits, I'm going to have 2 to the 8th, or 256 possible outputs. So if I start to change this k up, so k is going to be the size of my random list. So the chance of collision, so the probability that I have a collision, is then going to be given by 1 minus 256 factorial divided by 256 to the k multiplied by 256 minus k factorial. Again, you wouldn't actually want to compute those factorials alone because they would blow up and become obnoxious. So on the numerator, what you would actually see would be 256 times 256 minus 1 times 256 minus 2, all the way down until you get to this 256 minus k plus 1. So that last little term. So that's actually how you'd want to implement that, because otherwise you'd have this massive thing in the numerator, massive thing in the denominator, and you'd have to divide those. So if you do the arithmetic here, you can see some nice probabilities that are going to emerge. So if you give me a list of 16 of my quote unquote bad hashes, there's going to be about a 38% chance that I'm going to have a collision. If you give me a list of about 19 things, I'm going to be sitting right around 50%. And you can see that going up to 20 is going to tick that a little bit beyond 50 as well, which isn't very many. So it's, again, this weird paradox that's coming into play is that I have 256 possible outcomes, but simply having a list of 16 things is going to leave me with about a 38% chance of collision. If I get lists of 19 things, I'm going to be at about a 50% chance of collisions. If I'm up to 32 things, I'm almost up to a 90% chance of collisions. So that 32 is significantly smaller than the 256. And that's where that paradox thing is then going to begin screaming, is that you don't have to have 256 things to see some collisions. You can have far fewer than that. Is that it's hard to kind of wrap your brain around all of that. But if you step back and think a little bit, we're not specifically matching to one individual hash. We're not finding a birthday match. We're just finding general matches that are going to be living in these lists. If you scale this up a little bit, you can start to see that it's going to give us some information about where we should actually be living. So if you give me some hashing algorithm that's going to have an output that happens to be, let's say, n bits. So if you think about MD5, so MD5's output is 128 bits. So you have 128 different decisions to see on the back end, is that each of those can either be a 0 or a 1. So the total number of hashes that are going to emerge there are going to be 2 to the 128, which is a massive number. There's a ton of possible outputs that are going to exist there. But I don't need to study that many things in order to be hopeful of actually seeing a collision or some type of intersection between those outputs. In fact, if I take about the square root of that number, I'm going to get a pretty decent chance. So in the case of the bad hash, we had 256 outputs. So the square root of that is going to be this 16. And you can see in that scenario, we're right at about 38%. In general, if you take about the square root of n, you're going to have a pretty decent chance of finding a collision. So in that MD5, if I have 128 bits on my output, the total number of hashes are then going to be 2 to the 128. So then if I take the square root of that, it's going to kick out a list of size 2 to the 64th, should have a pretty decent chance of collisions. That number is still quite massive and fairly obnoxious to work with. So that becomes essentially unreasonable to work with. But if you were to scale this back just a little bit, you actually start to get some things that are not necessarily unreasonable. So if the output was only 64 bits, so if it was half, so if it was just these nice little 8 bytes rather than having 16 bytes, here you're going to see that there are going to be 2 to the 64th total hash values. And if you take a list of size, let's say 2 to the 32nd, you'd have a pretty decent chance of collision. This number is not so unfathomable to work with. This one becomes alarming. This one is not great to work with. It's kind of a meh face, but it's not the worst thing in the world. So it does kind of give us an initial breaking point of any reasonable hash algorithm. The output better be at least 128 bits. If it's less than that, a simple just paradox approach of having these lists and then finding collisions are going to be kind of open or kind of on the table as a potential attack on this thing. So this 128-bit output at least becomes the minimum that we should work with. We should tend to work with things that are going to be larger than that to give us even better security against these collisions, but that becomes the absolute worst kind of, or at least the absolute minimum that we should actually work with. So most of the ones that are in production obviously have at least 128 bits. Most are going to have significantly larger than that, but that's really where that number of 128 is going to originate from, is that anything below that's going to become susceptible. So we need to work with at least that size. So while we got a couple minutes, I do have a really quick just transition into some fun little computation. So if I swap my screen, what I have here is I'm going to play with our bad hash algorithm just a little bit further. So we saw that if I have a list of 16 hashed values, I have about a 38% chance of collision. So what I've done here is I've done just that, is that I'm going to create some lists of 16 things. I'm going to create their bad hash, and then I'm going to try to see if there are going to be collisions amongst that list. So what I have here is I'm going to have my bad hash as before. I'm going to have a function that's going to randomly generate words. And the way that I'm going to construct a word is going to be jamming together a whole bunch of letters and symbols, the number of which are going to range from 3 to about 19. And my symbols are going to range from capital A down to little z. But in the ASCII land, there's going to be some special characters that live between those. So some of our words might have some of those symbols as well. So I'm going to generate a list of 16 things. I'm going to then generate their bad hash equivalents. And then I'm going to go ahead and print out what those look like. So I'm going to have the index, I'm going to have the word, and then its corresponding hash value. And then I'm just going to ask you if there's going to be some matches amongst those. So we'll give this thing a run just to see if anything emerges. Probably need to reload this since I was talking beforehand and it needs to get all reset. So if I give this a fun little run, you'll see exactly that. So I'm going to have my 8-bit hash is going to have 256 possible hashes. I'm going to try to build a list of 16 things to see a decent chance of collision, about a 38% chance of collision. So on the printout side, I'm going to have 0 up through 15. The word that's going to emerge, and then the thing after it is then going to be what its bad hash equivalent is going to be. It's also kind of fun to see just random words reemerge. just because it's just vomit. So if you give this thing a rerun, you can see crazy other words reemerge. So we have cra in this scenario, or GINW. Sometimes they look like weird chemistry symbols that all get jammed together. In this particular run, we did actually see a collision. So entry 9 had a bad hash value of 1, 2, 3, and so did entry 10. So in this list of 16 things, there's about a 38% chance that I should have had a collision, and here we actually did see it. If I zero it out, I can try to run it again. This one, we had a whole bunch of collisions. So 12 and 15, 2 and 13, 7, 11, and 5 and 6. All of those things are coming up with some collisions, and I don't know if we got any super duper cute words that end up emerging. I like it when things like number 4 emerge that almost look like some swear words, so that I can just be like, oh, it wasn't me. It's just like a randomly generated word. So if I clear this out, hit some random generation again, you can see a couple more collisions. Man, we're pretty lucky here. It's only supposed to be about a 38% chance of success, and we're finding them like mad. Usually I do this in class and it's like fail, 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 fail. And then I have to like be like, no, it should work sometimes. And then I question everything about what's happening. So here we got collisions at 7 and 14. Obviously, both of those are going to have a hash of 42, and 14 also has a hash of 42. So what you can start to do is you can start to look at larger and larger things. If you wanted to change it not to be 8-bit hash values, but change that up to 16, obviously you're going to need a larger list to have some chance of collision. And that's exactly that little formula that we saw before, is that if I have 2 to the k as my overall number of hash values, well, then I'm going to have to take about the square root of that number to have a decent chance of collision. So that's where that number of 128 becomes our kind of minimum point, is that I need to have hash values that are at least that size. Otherwise, they're going to be susceptible to this collision or this birthday paradox attack. So I'll probably pause it there. We're going to then transition into actually looking into building some of these hashing algorithms that have 128 bits on the back end, so that we don't have this hopeful collision side of things. So we'll see a whole bunch of more XORing, going crazy, swirling and mixing and swirling and mixing. And then we'll see a couple cool things emerge after that as well. So stay tuned.